Okay, welcome back everyone. Uh, we'll just proceed with the next lecture of today. I'm very pleased to announce and introduce the next speaker of today, Dr. G. Bhaskar Raju. He is a former chief scientist of CSIR National Metallurgical Laboratory, Madras Center. He has over 36 years of experience in mineral processing and environment. And after his service in CSIR, he is currently working with so many projects in industries and organizations associated with mineral processing and environment. He has guided over 10 PhD students and have publications more than 200 to his credit. He has carried out around 69 or more projects in his research career. That includes Hindustan Copper Limited, Hindustan Zinc Limited, Kodarma Iron Ore Company Limited, Orissa Sands Companies, IREL, Indian Barrites and Chemicals, JSW, Gujarat Mineral Development Corporation, Bharat Starch Industries, so on and so forth. He is a member of so many academic and professional bodies. Naming a few is Indian Institute of Mineral Engineers, Society for the Advancement of Electrochemical Science and Technology, fellow member, Institute of Chemists, India fellow. He has so many awards to his credit. Naming National Mineral Award from Department of Mines, Government of India, Mineral Beneficiation Award from Indian Institute of Mineral Engineers, and CSIR Technology Award from Ministry of Science and Technology, Government of India. Actually, the list goes on, but I will just make it short and ask Bhaskar Raju sir to please start with his lecture. Sir, please.
Thank you, Dr. Ashita. And today we are going to have an introductory type of lecture on zeta potential measurements, a tool to understand the interactions at the solid solution interface. See, most of the chemical reactions which we cannot see by naked eye, but this zeta potential measurement can, we can visualize what is happening at the solid solution interface. Suppose if you put some solid material, any of the water or any of the solvents, what is happening at the interface level, we can foresee, we can visualize by zeta potential measurements. Next, going to the applications where this zeta potential knowledge is very important is that very useful in preparing the colloidal dispersions such as paints, inks, pharmaceuticals, cosmetic preparations, and food products, and so on. See, for example, if we look at paints, so paints may be a solid or solid dispersed in some solute or some solvent. So when the solid is dispersed in either in water or in some solvent, it should be properly dispersed. That solid should be properly dispersed so that it will be very useful while we are doing the painting. So otherwise, if it is not properly dispersed, what happens is the solid will get separated and solution, the whatever is the, it is on the either in water or some solvent will be on the top of it. So to avoid that, a proper dispersion can be achieved by with the knowledge of this zeta potential measurements. And also some of the cosmetics, which are, a solid dispersed in some liquid, these cosmetics also can be prepared in a finely dispersed state so that we need not have, for example, even in some of the, health like magnesium hydroxide or whatever it is, such kind of things also can be properly dispersed and they can be applied to the whenever it is useful. Next one is in barite, is an useful chemical in the drilling mud. This in barite is a mineral. This barite is extensively used in the drilling operations of the oil. While doing this drilling, this the barite should be in a slightly thixotropic state. That means slightly solidified state, so that when pumping, it should go to the fluidity state. Otherwise, it gets struck. The drilling will get struck. So to predict that condition, we can use some small peptidizing agents such as polyphosphate. So how much of polyphosphate is required and how to achieve that can be known from the zeta potential measurements, zeta potential knowledge. Similarly, coagulation or flocculation also can be, if we have some knowledge of the zeta potential of such kind of solid particles which are suspended, we can have an effective coagulation and flocculation. And similarly, to predict the mechanism of adsorption, suppose some particles when we put inside the water or in some solvent, what is happening at the interface of between the solid particles and the liquid phase, we can visualize, and we also can predict what type of reaction that is taking place, what type of adsorption, whether it's a simple chemisorption or physisorption or such kind of things also can be predicted by this zeta potential measurements. It is like that we can have this zeta potential measurements knowledge in most of the industries and applications. We can formulate the proper material with the knowledge of this zeta potentials. Now, before going to the zeta potential measurements, we should have some knowledge about the dispersion of colloidal particles and what are the forces that are acting on the dispersion or flocculation. So we have broadly we have two different types of forces, that is attractive forces and the repulsive forces. These attractive forces are the van der Waals attraction. They are all very short range. They operate within 5 nanometers of between the particles, a distance of 5 nanometers, something like that. And similarly, but these van der Waals attractions are very weak. And then it is, these van der Waals interactions are very temporary. It is not very permanent. Similarly, hydrophobic interaction also. The best example for a hydrophobic interaction is you put a butter in the water and then how the butter will be collected at the top of it without any this thing. Similarly, next thing is repulsive forces. How these repulsive forces, what are all the repulsive, what is the repulsion that takes place? What is that force that will be separating two particles is, one is electrostatic repulsion. So electrostatic charge will be developed. Suppose if two particles have the same charge of either positively charged, they get repelled with each other. So these are the repulsive forces. Similarly, steric forces also, steric hindrance. So because of steric hindrance also, the particles will be properly separated. Then going to this van der Waals forces, this is the weak forces, as I have mentioned earlier, that the attractive forces or because of the van der Waals attractions. For example, if you look at it as simple atom or particle, whatever the way you take it, this particle, because of the fluctuations in their movements or fluctuations in the electronic cloud, this electronic cloud will get polarized. For this a temporary phenomenon. When this type of polarization, all these are the electron cloud, these are all the electrons. When it comes to the one-sided, this is a negative force, and then this is nucleus is a positive force. Like this, when it happens, immediately it attacks the another one, like also to polarize. This is a negative sides, and also this positive sides will be polarized like this, and negative will be like this. So when it happens like this, there will be an attraction between a negatively charged particle and a positively charged particles. So the attraction between these two, this is a simple van der Waals forces, but it will be a temporary phenomena. It gets again separated, but at the same time, it happens when the particles are approaching something like 5 nanometers or less than that. Beyond 5 nanometers, these forces are no more applicable. Then the other one is the hydrophobic interaction. Hydrophobe means which is non-wettable with water. So suppose if you have the butter finely dispersed in the water, it will be in this state. And when you want to make it join together or flocculate or whatever it is, you can join by hydrophobic interactions. Of course, this was well established by this entropy factor and enthalpy factor. When the entropy, of course, every one of you is know is a term related to the randomness, and then this an enthalpy is related to the heat in the system. And then when this entropy and enthalpy is negative, and then delta G, free energy, is positive, you can have this type of things. Suppose if we change it, we can change it. There is an entropy to positive and enthalpy to positive, and the delta G will be negative. It will be coagulated like this. That means this water molecules will be squeezed out, and then this hydrophobic part will come and join together. So like this, you can improve the coagulation of the hydrophobic substances when it comes to the wherever the reactions of such kind of materials are taking place. Then when we go for a repulsion, that is two types of things are there. The electrostatic repulsions. When electrostatic repulsions are nothing, but these are long range. It can have more than 5 nanometers, or even at something like 100 nanometers also it takes place. These repulsion forces will be taking place when, suppose if this is an atom with a positive charge, and then another atom or a particle with a positive charge will get repelled with this thing. And then this is DLO theory is there, which has explained, in a comfortable way, how to these both the particles will be repelled with each other, and similarly how the attraction will take place. So all these things were explained in DLVO theory, which you can follow it up. Then steric repulsion. There is another way also is there, that you can suspend the solids in a by steric forces. Suppose if this is a particle and you have the adsorption of some polymeric molecule on top of it. These polymeric molecules will, they will separate these two particles not to come very close to each other. Just because of these things will interfere, and then the suspension will be in a very finely suspended state. They don't come close to each other, so that they will be suspended. So this steric repulsion or inhibition will take place via these long polymer molecules. So this this is also one way to improve the repulsion between the two particles. So why I am telling all this repulsion and flocculation is that whenever there is a solid substance, or a solid is put into the water or something like that, we have to create either, if we want to create a suspension of that. Suppose if you have something like A, B, C, D of some 10 different materials. Maybe, when the 10 different materials are there with the different charges, you can also what happens is, if there are some 10 different materials with the different charges, they may coagulate, or they may join together because of these other forces. But at the same time, if we have the knowledge of zeta potential, we can disperse them in a fine way. Suppose if all the particles are negatively charged below a pH of 2 or 3 or something like that, so you adjust the aqueous pH to something like pH 2, the entire system will go to dispersion state. So the particles will be separated because all the particles are negatively charged. That can be achieved by adjusting the pH. Similarly, the negative charge also can be, other side also can be you can go even pH where all the particles are negative charged. Suppose when the negative charged particles means you go to the extreme basic conditions, alkaline conditions. At that time, negatively charged. Even at that time also, the particles will be completely negatively charged. And then when all the particles, or 10 different particles, all are negatively charged, you can have a perfect dispersion in the, all these particles will be perfectly dispersed in the water. So that is how it is achieved. But with the knowledge of the zeta potential, we can formulate such kind of things using those, how to disperse given a material. So if that material zeta potential things are, we know that we can disperse it without even looking at the things. So the knowledge of zeta potential we can use for the dispersion and flocculation of various materials. Now, even also some of the things which I want to go before the introduction of the zeta potential is there. This absorption of all water molecules at the, suppose if this is a water molecule, this gets this as an H3O plus and OH minus, it gets dissociated. Now, the most of these metals or metal oxides or minerals will be in the form of mineral or metal oxide. Sorry. So this is a metal oxide, metal oxide. This is a surface. This is a surface like this. When you have the metallic strip, it will be in this form, or mineral, for example, molybdenum or titanium. So this metal, titanium oxide. So molybdenum oxide, something like that. Iron oxides. All the M stands for metal, O stands for oxide form. So when it is like this, the surface is metal oxide, oxygen, metal oxygen. When it is like this, these water molecules will polarize. Metal will be always having a positive charge. So they attract the negative charge. Negative charge is this OH, water molecule. When this water molecule goes, this will form MOH, and then this will form OH, because this H plus is a positive, O is a negative, it forms as a OH. So the water molecules will be, aligned in such a way that they get dissociated into this form, and this oxygen, since this oxygen happens to be a negatively charged, all the H plus will be attached to this, and all the OH minus will be attached to the metal atoms. So you can have a situation MOH, OH, MOH like this. So it gets neutralized. The entire surface will get neutralized with OH and H plus like this. So this is how, even for any material, the moment you put it into water, it will either dissociate or dissolve. Sometimes it will dissolve also. Some of the metal ions will come into the solution, or some of the oxygen also you can remove from the solution. So you can develop a surface whatever the way you want, whether your surface should be positively charged or your or it will be negatively charged. We can create such kind of conditions by with the knowledge of zeta potential measurements. So now, for example, if you have a molecule like this, where the acidic groups are, for example, any of the oleic acid or such type of acidic acid or some, when it is like this, you can, all these H plus ions will be dissociated, and you can create a negative surface charge. When it is in operation, you can create, if you take it to a basic conditions, you can, this will be in the form of COO, either in the form of Na or like that, the H plus will be released. So this will be negatively charged surface. Similarly, you can have the OH group. When the OH groups are there, by taking out these hydroxyl groups, you can create a positively charged surface. So you can play with the, so this is a, here I have shown it as a plate like thing, but you can presume it as a particle also. This will be a particle. Around these particles, these OH groups will be this thing, and by neutralizing those things, you can get it out, and then you have the charge development of positively charged development on the surface of the particles. Suppose if materials like silver iodide and all those things, if you put it, whether this way also, by this happens by dissolution. Suppose if silver is getting coming into the solution, you have a negatively charged surface on this. Similarly, this silver iodide, see iodine, if you take it out, this can generate a positive charge on the surface. So depending upon the things, we can create a positively charged or a negatively charged, or on its own, it can develop either positively charged or negatively charged, depending upon the pH of the solution. So this is another way of developing the cationic surfactant. Suppose a surfactant which is a cationic thing, for example, amine, primary amines are all, R and H3 is a cationic. So when this will absorb on the surface of any material, it is a positively charged surface. We can generate. We can generate it. It is not only for what I'm talking. This already told. You can assume it as a particle which is in a spherical shape or in a plate or whatever the way you want. So when the particles are adsorbed with cationic surfactant, all the particles will be positively charged. So when all the particles are positively charged, they will be dispersed in a dispersion state, and you can achieve the dispersion among the particles. Then coming to the anionic surfactant, that is, some of the sulfonates. Sulfonates are there. These are the anionic surfactants. When these type of surfactants are absorbed on the either these particles or this plate-like structures, you can have a surface with negatively charged surface. You can have. Why we want to create this negatively charged surface or positively charged surface means the material which we want to absorb on that again should go into these conditions. Means suppose if this kind of things are there, we need a positively charged substance to go and again join this and make a coating of like this. When the coatings, if we want to apply for this, we should have a thorough knowledge of the particles or the surface of the material, so that we can try to absorb our what type of material can absorb on the surface of these materials. Then before going to this, we should have some electrical double layer models also. We should have some knowledge on this. So this is an electrical double layer. Why electrical double layer means what we are the zeta potentials. In order to understand the zeta potentials, we should know the electrical double layer, how exactly this electrical double layer is being done. Suppose, for example, when these particles or surface is positively charged. So this is an Helmholtz model. He says that all the negatively charged from the solution phase will come and they will try to neutralize between this positively charged side. All these negatively charged molecules will come, and then there will be a sudden drop in the voltage. Okay, there will be a sudden drop in the charge between the surface and these things. Because of the absorption of this, there will be a sudden drop and come to the zero state. Zero or some negative charge, but the negative charge will be, positive charge will be reduced by adsorption of these things, but they are very close. And then Helmholtz model, what Helmholtz model says is they are firmly attached near to the surface. It's a condenser type of thing. But then at a later stage, since it cannot explain all the factors, another thing, Goy and Chapman has independently proposed a diffuse double layer. In this diffuse double layer, what happens is, suppose if this is a positively charged surface, and the first layer, I mean, it is not turned as one layer. It can be maybe when it is very nearer to that, some this negatively charged will be, some will be very nearer to that, but the charge, it will diffuse over an extent of some distance. All this negative charge will get negatively charged particles. Even from this, it acts, and then so this type of electrical double layers will be formed. That means here it will be a sharp drop across when this particular negative charge is neutralizing. When this thing is there, it will be over a distance. This will the positive charge will decrease by the adsorption of negatively charged particles, but it is over a distance. And the third model or something like sterile layer also is, Stein Graham also has proposed yet another model. That is, he put this one is this same Helmholtz model, he has divided into two planes. One is these particles are, these charges will be very firmly bound to the surface. And then in the next layer, these things will be mixed up. These things also will be there in the next layer. And then at the in a diffused state. So he divided this Helmholtz thing into two. This is inner Helmholtz plane and this is an outer Helmholtz plane. They are very firmly bound to the surface. And then when it is over and extended, this may not be that firmly attached to the surface. But however, they will help in neutralizing the surface. So there are nearly something like 6 different models, electrical double layer models are there proposed by different scientists. Now let us look into the what exactly is the zeta potential. So as I have explained the electrical double layer, suppose you assume that this is a one where it is a negatively charged or whatever it is, around this a positive charges will be absorbed. And then this positively charged also in the second layer as I proposed in the Stern model. These are the absorbed things. But at this place, electrical double layer is up to this place. So this Stern layer is something like up to this. This is a Stern layer surface. This thing Stern potential. And then at this place, this particular place, whatever is the potential, that is called zeta potential. Why we can measure is this is zeta potential is nothing but a shear plane that will happen at the shear plane. Shear plane means suppose when this entire particle is moving this side and that side, these particles will lag behind the particle. So this at this particular surface, whatever is the potential that is available that we can measure. This is a surface potential we can say, but this we cannot measure, whereas this can be measured. This is called a zeta potential. Zeta potential is because of zeta potential is a scientific term. This is an electrokinetic potential in colloidal dispersions. It is usually denoted by a Greek letter zeta. Hence, zeta potential, the usual units are volts or millivolts. So, once again, I wish to stress that the potential which we are measuring at this plane is shear plane. This is called a shear plane. That means when the entire particle with the surface charge, all these things will be going along with the particle, whereas beyond this type of charges will lag behind. But they cannot firmly this thing, but at the same time, they will be nearer to the surface, but the lag behind. This particular potential is called zeta potential. The potential at the shear is called a zeta potential. So we can exactly measure that particular potential. Now, the stability of when coming to the stability of the suspended particles is that suppose when we measure the zeta potential with reference to the various pH conditions. Okay. Now, the zeta potential, suppose if we take a 2, it is something like 30, 40 millivolts. And then when the things are going, it will come down. And then at this place, it is 0. This is called isoelectric point. Then that means where the particle will have no charge on the top of it. And beyond this again is negatively charged. This is 30 millivolts. So when the pH is increased, this zeta potential values also will be increased. When it is when this is unstable at this stage, when the particles are 0, isoelectric points, they cannot be dispersed. Whereas the stable dispersions can be achieved above 30 millivolts. Similar at the bottom, positive plus the 30, or here also at the bottom size minus 30 millivolts, you can achieve the stable dispersion. That means when the particles will have a zeta potential of about 30 millivolts, you can expect a stable dispersion in the, you can suspend them in the liquid. So then next followed it by how, what is the zeta potential then? Yeah, here it is 0 to plus or minus 5 millivolts. It is a rapid coagulation or flocculation. That means it won't be there. And then 10 to 30 millivolts incipient instability. Just slightly it will become unstable. And at 30 and 40 millivolts, a moderate stability. And then 40 to 60, good stability. And above 61, above 60 millivolts, there is an excess. When the charge will be very high on the surface of the particles, they get properly dispersed so that you have the fine stability of dispersed particles in the liquid medium. So this is how the extent of zeta potential we need to develop on the surface of these particles. We can manipulate this zeta potential. What is the required zeta potential by manipulating the either the pH or absorption of some reagents over the top of that. Yeah, then the coagulation and then flocculation. This coagulation and flocculation also, this knowledge also we can see. This coagulation means it is usually the inorganic salts by putting, for example, inorganic salts like alumina or iron oxides, iron ferric hydroxide. All these things will be useful for coagulation of alum. Alumina is nothing but an alum. So when you use the alum or ferric alum, these coagulations can be achieved. And then they are the very strong forces between, energy barrier is very high. That is why it gets compressed. So the second one is flocculation. Flocculation can be achieved by using the flocculants, lengthy molecules where they will get absorbed and then they get flocculated. They get bind over the entire, the entire molecule, and then you will get a flocculation mechanism. See here, when it comes, this again is a DLO theory. When a primary minimum, this is the primary minimum where you can achieve the coagulation, and then this secondary minimum at this place you can achieve the flocculation. That means the energy required for flocculation is very less, whereas at the primary level means you need to cross the barrier and you need more energy. So this flocculation can be, you can, if you want, it can be reversed because it is not that stable. You can reverse the condition to backside to the coagulation. Now, for example, if you look at it, these are the particles, all are negatively charged. So you are introducing some positively charged salt into that. And then when it goes positive, the charge will get neutralized and then it will form flock like this. All the charges will be neutralized and then it forms a flock like thing. Inorganic, as I have mentioned earlier, either alum or ferric alum can be used in this part to achieve these flocks. Suppose if these flocks, if you want to make it as a bigger one, so these flocks, you polymeric flocculants, if you use it, it will make a bigger flock, which can settle down very easily. So the flocculation is mainly basically achieved by a polymer molecules by absorbing those polymer molecules. So how this is depending is, again is we are talking about, if we know the particles charge, we know what is the material, what type of flocculants to be added, and all this knowledge can be based on, again is a zeta potential of the particle. So now we have come to the actual zeta potential. So this zeta potential is the migration of charged particles or molecules under the influence of electric current. So here it is anode and cathode. You have put two different electrodes, and in an electrolyte is a must. Electrolyte means you should have a conducting solvent. Either it can be sodium sulfate or it can be sodium chloride or it can be some conductive solvent you have to use, or in a water you put some either salt or sodium, a simple table salt like sodium chloride or sodium sulfate or something like that. So it will become a conductive. So in that conductive medium, all this positively charged and negatively charged, any material if you put it, it gets in this state. The moment you apply the power to this thing, electrodes between the, when it is connected, both the things, and apply power, these, suppose if this is a positively charged, this is a positively charged means cathode, all the negatively charged things will come to this surface, and then positively charged things will be moving to this electrode. So a net, this thing, I mean, the moment you apply the voltage across these two electrodes, both the things will start moving into different directions, whatever is the direction that. Suppose if you have a single mineral or whatever it is. So why I am telling is, if your material has got different things, then it will become very difficult to measure the zeta potentials. Zeta potential is basically useful tool to measure only on pure materials. So it should have only one charge. Suppose that means a metal will have only one charge, either positively charged or negative charge. So when you put such kind of material into this, they will move either to the anode or to the cathode. And then when it is moving, the things which we can see the microscope and measure the velocity, how much velocity they are going through the liquid, and then it automatically gets the velocity of the particles, and from the velocity of the particles we can calculate the zeta potential. Yeah, actually this is the one, microscope here. This is an yeah, this is the thing like this. See, what you have is you fill your a particle suspended in electrolyte into this thing. This is a capillary tube inside. This is a capillary tube. And then in this capillary tube, a microscope will be projected. And this is one electrode and this is another electrode. These electrodes are connected to here, and then you connect it, yeah, to this zeta meter like this. So this is the one where you are putting your suspension of the material. Your material is suspended and in a slurry form you put it. Just it should be very very dilute, maybe something like 0.1 gram in 1000 ml, something like that. You can put it so that you, and then when these electrodes, you can put it back and connect it to the zeta meter, and it will show the reading. And this will be in whole things. If you want, the is a typical microscope. And then this one is also is, nowadays there are different varieties of instruments that have got a screen where all the particles are moving. Instead of looking at this microscope, you can see a screen where all these particles are moving to one particular direction, and then what speed they are moving, and everything will be noticed. So once we measure that things, here is an equation which gives the zeta potential. In nowadays, in most of the equipments, a direct zeta potential. What is the zeta potential? At the end of your measurements, it gives the zeta potential. But usually we take something like 10 readings and take an average of it also. Such kind of provisions will be incorporated inside that. This is Henry's equation, and then this particular thing is, this is an electrophoretic mobility, and then this epsilon is a dielectric constant, and then this is zeta. This is actually zeta potential, and then n is a viscosity, and then this is an Henry's function. So from this equation, you can measure the zeta potential. Yeah. So what the measurements, what we are doing, whether it is right or wrong, we have to check with one such measurements. For example, you put all the particles in different concentrations of, I mean, when you suspend this, I mean, any of these powders, solid powders, you put in potassium nitrate of different concentrations, 10 power minus 2, 10 power minus 3, 10 power minus 4. And then when it is measured that at different things, you measure. See, for example, this one belongs to the 10 power minus 2, highly concentrated. And the next slightly diluted condition, you will get this type of graph. Another slightly diluted condition, 10 power minus 4, you get this type. But the point of zero charge, isoelectric point remains same. That is at a given pH. This is at pH. IEP is pH 6. That means at this point, the particles are maybe negative, I mean zero charge, no charge on the surface of these particles. Whatever the way you, with this concentration should not affect your measurements of this zeta potential like this. So it should have one isoelectric point. See, when you increase the concentration or ionic strength of potassium nitrate, you get this. This is an electrical double layer from here to here. This is entire electrical double layer. It gets, when you increase the ionic strength, that means this the solvent, I mean where you have used the electrolyte. So more the electrolyte, this double layer will be condensed. That means the distance between the surface and your molecules absorbed will be compressed. So this will be shown as an Debye length. So what is the Debye length? You can exactly estimate how this, by increasing the electrolyte concentration, it gets electrical double layer will get condensed. Then that means, see, all these operations we are looking at a surface of a few nanometers difference, which means we are exactly looking at the surface reactions. What is exactly happening at the surface of any of the, either of the particle or any of the material on the surface of the particles. Zeta potential, even though it directly don't reflect on the surface of the particle or this thing, but it gives near to the surface a few nanometers away from this surface, but it gives a clear cut what is happening at the interface level. Also there are two terms in this: point of zero charge and then isoelectric point. See, the point of zero charge. Now let us go to this particular position. For example, here, this is, you have different concentration of 10 millimolars, 100 millimolars, and 300 millimolars. You have performed the zeta potential things and different ionic strengths. So you have it here. So you have used potassium KNO3. In this case, lithium nitrate. So what happens is, here it is, whatever the way you do it, this point of zero charge is not, it remains, isoelectric point remains same irrespective of the concentration of it. Suppose in this particular case, lithium nitride, this charge, it is varying. I mean, this isoelectric point will get shifted to maybe a few pH points. So which means this is interfering at the interface. In other words, the electrolytes which we are using for the conductivity measurement, conductivity purpose, it should not interfere in the interface. I mean interface or it should not absorb on the surface of the particles. So in this particular case, potassium nitrate, we can clearly say it is not interfering in, it is not absorbing and changing the isoelectric point. Whereas if lithium, if you use it, because of its small molecule, small atom, it interferes in the interface. So we should not take this type of electrolytes into consideration. So first of all, we should ascertain before measuring the zeta potentials whether this particular electrolyte, okay, whether this, for example, sodium sulfate, this potassium nitrate, or sodium chloride, whether they are interacting with our material. If they interact with our material, they are not very useful. We have to use the electrolytes in such a way they are called indifferent electrolytes. That means they don't interfere with our interface. They will remain and provide the conductivity. That's all. Otherwise, these ions doesn't move or absorb onto the surface of our particles or to the surface, whatever it is. So we have to choose only such type of electrolytes. Maybe we are in the regular form, this potassium nitrate is being used, and then sodium sulfate also is being used, and also some instances. So I mean, this sodium chloride also we can use it for conductivity. But at the same time, it should not reflect or it should not get absorbed on the interface. So indifferent electrolytes we have to use. Once we ascertain that they are not interfering, the same electrolytes we can use it for our zeta potential measurements. Now let us look at the how the, for example, this is the silica. Any material, silica material, when you put it into the water, this is an equation like it forms a positively charged ion SiOH twice plus at very low pH of say something like around 2 or 2.5. This is positively charged potential. And after that, say at this pH, after this pH, it is negatively charged. That means it is SiO minus. This SiOH at this place, exactly at this place, 0, it is in this place, it is in the form of SiOH. There is no charge. Below this pH, it is in the form of SiOH2 plus. And in the alkaline conditions, you have this SiO minus form. So silica or silica particle can be available in 3 different states depending on the pH of the electrolyte or whatever it is. So SiOH2 plus in the acidic condition, it is in this form. And suppose if you want to absorb this material, what happens is that this is primary amine, a long chain, a primary amine. This primary amine, by shaking with these particles, you equilibrating with this SiO2, you can have this absorb. All this negative charge will be shifted to the positive charge. Why? Because it absorbs on this SiO and RNH3 plus. This will get, and then this will reflect RNH3 plus conditions. So this will be in the positive surface. But when RNH3 at the below pH 10 and all, this it will be in the form of RNH2. So it is no more in the form of NH3 plus. It will be converted into amine, a simple primary amine. So there won't be any interaction with SiO surface. So as long as this is SiO, this thing, and then electrostatic attractions will take place, and you can create either a positively charged surface or you can neutral at this point, neutralize the entire SiO with this at this point. Suppose if you want to work somewhere in the not in the acidic conditions, if you want to work it in the basic conditions, you say, I mean, SiO molecule, you can neutralize by adding this RNH3 plus. So why this thing is, this particular application is in the flotation. When we want to separate the silica particles, we use this primary amine as an reagent. This primary amine will coat on the surface of the silica particles, and when the air bubbles we press, this silica will be separated from the remaining particles. So thus it is useful in the separation of silica from the other materials. The other materials means silica. Suppose if you have the other materials also in this thing, they also will have different things. So you choose in such a way that only silica is negatively charged and then this is positively charged. So other things will be positively charged. You select that particular pH so that you can achieve the selective adsorption of this amine onto this silica surface. Why this amine you float is this? This is a long chain hydrophobic molecule so that you have the hydrophobic nature once it gets absorbed on this. So it gets separated by attaching to the air bubbles. Similarly, this zeta potential of alumina. This is an alumina. When you take the measurements, this particular at this pH, this is alumina is in this form AlOH. That means around 9.7. It is neutral. Alumina is no negatively charged or positively charged. It is in this form of AlOH condition. And below this pH, it is in the form of AlOH2 plus, and then beyond this pH, it is AlO minus form. So why I am talking is, if you want to adsorb, you can change the surface of this alumina into different forms. All this by changing this, or if we know the PZC of this particular alumina, we can predict. So we can accordingly add our material for the adsorption of what. Suppose if something we want to adsorb on this, suppose if you want to choose work at this pH of 8. So you know that it is in the form of AlOH plus. So if you want to adsorb, your material should be negatively charged. Whatever you want to absorb on this alumina, at this conditions at 8 or this thing, you have to use some negatively charged substances. So similarly, when it is a titanium, this thing, titanium also at this place, it is neutral. It is in this TiOH form. And then it is at this place, it is TiOH2 plus form and then TiO minus form. Yeah, zeta potential of graphene. So graphene is an, it is a network of this carbon, but at the end of these things, if you look at it, at the end, you have the carboxylic acids. So when the acid carboxylic acid H plus is removed, it will be negatively charged. So in other words, all this graphene will exhibit a negative charge. And it depends on the, your zeta potential values also depends on the particle size and also pH. Suppose this is a particle size measurement. This is a particle size. So if you look at around say 500 nanometers or at this range, it will be 5 microns or 0.5 microns range. At this pH, there is no change at this pH, and it will be 60 millivolts. Zeta potential will be 60 millivolts, and as it goes the pH down and down, it will be less and less of the negative charge. Similarly, if you look at the zeta potential of these things, this thing, and then with reference to the particle size, this particle size at 500 microns, the zeta potential, that means the less the particle size, you have the more zeta potential. And particles, when it becomes a bigger and bigger, a little bit bigger, but any of these zeta potential measurements, you cannot take it to say something like the particle size should be within say 10 to 20 microns. Beyond that, it gets settled on the tube. So we have to invariably measure the particles below 10 microns range. Now, similarly, the fluoride surface. Fluoride is, I have taken invariably the inorganic materials because you come across these inorganic materials very frequently. And also, I am a mineral engineer, so I have the data mostly on these minerals. Fluoride is nothing but calcium fluoride. How this calcium fluoride, why we measure this is the sulfuric acid we want to absorb on this, and or otherwise citric acid we want to absorb on this. So we should know what is the zeta potential of fluoride. This is the actual zeta potential of fluoride, which means at pH 9, it will be 0, and this is negative at this. So if you want to make it, when you are absorbing, the entire things will become negatively charged, either at different dosages of sulfuric acid or citric acid. The zeta potential will become negative. That means, in other words, you can say this is observed. Why this negative charge is creating on this fluoride surface, even though it is at it should so, then that means you can say some of the sulfuric acid is absorbed on this. That is why it is showing the negative charge. So you indirectly you can say whether some material is absorbed, if that material is what type of material. So it should be a negatively charged material. That is why you are seeing the negative potentials. So that is another way of doing the thing. So if we, when we measure this thing, so we can see that some other material is absorbed. So when that is some other material is absorbed, so you can have a different zeta potential on this. And another also we have a different things in when you put some of this is some of the same silica, if you take it, and also you put some metal ion onto the surface, it gives you will get this type of zeta potentials. It will get two different reversals. Which is the meaning is that suppose it is not only SiO or SiOH, you take any material, over that material if you put any of these metal ions, for example, as I mentioned, this calcium, I mean copper. This is a species distribution diagram where I have shown this copper will be in the form of Cu2 plus somewhere around this. This is the line which comes, and then it is in the CuOH2 and CuOH plus and Cu. It will take different species depending on the pH. You more the pH you will go, it will be converted. Cu2 plus will get it converted into CuOH and CuOH twice, and then CuOH thrice minus CuOH 4 times 2 minus, like this. So this type of condition also we can, when some metal ions are absorbed on a given material or not, we can find out by this type of material. Suppose in this particular case, I have taken the silica. When at this pH, the silica is SiO minus, and the metal will be in the positively charged. When this is the one. When I am absorbing the metal ion, when the metal ion gets absorbed on the metal ion is a positively charged, so it is a negatively charged, it gets absorbed. So when it gets absorbed, you can develop the positive charge on the surface of negative beyond this way. And then when you increase further, when you increase the further into a basic side, this metal ion will get again hydroxyl ions will get absorbed and it will become MOH. This is an MOH surface. So absorption of metal ions on any surface also you can predict whether these metal ions are absorbed or not. You can also see this type of, you can predict in this particular, these are all very essential things when you are separating different particles from the slurry. These type of situations you could able to foresee and then predict. So when it is metal ions are absorbed, instead of one, you have several things. PZC1, PZC2, point of zero charge 1, point of zero charge 2, point of zero charge of this one is 1, and when it becomes MOH, this is another one, and when it is SiO, MOH, I mean when it gets neutral, it will form like this. So you have different PZCs, that is point of zero charges, and then ultimately when it is in this condition, it will be again coming to the negatively charged. And finally, why this is, we also can predict what type of interaction is taking place on this cell. Suppose when we introduce certain reagents into the, solid particles, whether that reagent is absorbing or not. If that reagent is absorbing, what type of absorption that is, whether it is a absorption or it is a chemisorption or some other absorption process, that also you can predict by taking an elaborate experiments on that. In this particular situation, I have tried the oleic acid into the sillimanite. Sillimanite is aluminum silicate. So I have used the oleate, and then when it is adsorbed on this sillimanite, okay, your zeta potential point of zero charge IEP values will get more the concentration. If I take, it is getting shifted to this thing. So you can observe the shift in the pH. You can observe the shift in the pH after the absorption of these things. It is not isoelectric point. You can observe isoelectric point 1, 2, like this. Shift in the isoelectric point. This is the actual point of zero charge for the original molecule. When you are using 3 different concentrations, the isoelectric points will be shifted to different pH values. Using this shift in isoelectric point, we can predict whether it is a chemisorption or a physisorption or any of these type of adsorption mechanisms we can predict. So this is an electrical based on the electrical double layer model. Dr. Pradeep and all those people have developed this type of equations where you can find out the final thing like like this. It's a delta pH, that is, this is the pH. What is the shift in this pH? You will be knowing it experimentally. You will be knowing because this shift in pH can be noted. And then this is Z is a valency of the reagent which we have used. Maybe CO, for example, oleic acid valency is RCOOH. So valency is 1. This is a Faraday constant. This is a Gans constant, temperature, and this is this one is a dielectric constant of the material which you have used, so that delta G specific adsorption you can find out. This tau m is adsorption density of oleic acid on sillimanite. By measuring the adsorption of these things, how much of material, oleic acid is got adsorbed on the surface of sillimanite, we can measure. We can measure by other methods. So that amount of oleic acid adsorbed onto the measurements, this is so many moles per centimeter square, something like that we can measure. This is adsorption density expressed in moles per centimeter square. So this delta G specific can be, this is an initial concentration of the oleic acid, the C0, so that we can ultimately measure the shift in IEP. So IEP values at different things. What is the value? This is the oleic acid concentration. This is a term, and then you can exactly find out what is the delta G values. This is 8.12, 9.97, 7.79, like this. So this, in other words, we can say if the delta G is more, say something like 20 kilocalories per mole, then we can categorize as a specific adsorption, specific interaction is taking place. Or otherwise, this type of things, maybe even if it is not an physisorption, you can say a weak interaction between sillimanite and the oleic acid. So this, by knowing this delta, calculating these delta G values, we also can predict what type of interactions that is taking place, whether it is a specific interaction or it is a weak interaction between the substrates. Of course, these are all some of the materials where the isoelectric points are given. So you have the vanadium oxide 1.5. That means vanadium oxide at pH of 1.5, it is a neutral. So silicon dioxide SiO2 at pH 2, around pH 2, otherwise manganese dioxide around pH 3, and then when it comes aluminum 9, iron oxides 8, so titanium dioxide 6.2, Tyler this thing, and lead oxide 10, like this. So this data is very useful for us when you want to separate one particular material from a combination or a complex material with having so many, I mean, with different IEP values. If you want to suspend 10 different, minerals in a condition, you can suspend it, taking the entire mineral, all the minerals into the same, possessing the same charge, whether it is positively charged or negatively charged, you can disperse it. Once it is dispersed, by adding a selective reagent, it can diffuse onto that particular metal and then absorb on that particular metal, and it coats on that particular metal, so that it can get separated from this complex situation of 10 different materials present in the aqueous suspension. So like this, the zeta potential measurement, knowledge of zeta potential is very useful. And then we mainly in the process of separations, whether it can be in the mineral processing, so different minerals, separation of different minerals, paints, and then even wastewater treatment also, the knowledge of zeta potentials will be utilized, and then you can plan to achieve a perfect dispersion or perfect flocculation and coagulation. So with this, I would like to end my lecture. Thank you for your hearing. Any doubts means you can express or you can ask for it. Thank you so much.